This video contains the solution for AP Physics C 2007 Mechanics problem number 1. In this problem, we have a block that is being pulled along a surface with friction. Problem is right here. And see, force F1 acts at an angle theta to the horizontal, as indicated above. The acceleration of the block is a sub 1. Express all algebraic answers in terms of m, F1, theta, A1, and fundamental constants. On the figure below, draw and label a free body diagram showing all the forces on the block. Please understand that when they ask you to draw a free body diagram, they do not want components of forces, they want the actual forces. So we have the gravitational force, frictional force, this F1 pulling force, and there's something missing. There will be a normal force, right? The box will weigh something, or the ground will be pushing up on it. And you might think you're getting a little bit ahead of ourselves here, but would it actually match the force of gravity? In this case it wouldn't, because F1's pulling up a little bit, and remember, if somebody pulls up on you a little bit, it makes the reading, if you're standing on a scale, it would make you seem lighter, and that's the normal force. So the normal force would be a little bit smaller here. I don't think that they awarded or didn't award points for the relative length, but to be accurate here, that would be smaller. Okay, part B. Again, let me just restate that we should not have the components in this drawing, right? The force is this one. Now later on, if we want to break it into components, we can, but on the free body diagram, we should just have the forces acting on it. Okay, in B, we want to derive an expression for the normal force exerted by the surface on the block. Okay, so this is number 1B. We have, now I'm going to break the force into components. So I've got the force of gravity, which is mg. I have the frictional force. Well, frictional force doesn't really matter because it's in the x direction, but I'll put it in here anyway. We'll probably need to talk about that more later. And then the pulling force, F, can be broken up into F1 cosine theta and F1 sine theta, and then the normal force would be here, right? So that's all the components broken up and all coming from the center of the block. So I think we can see, since the block is not doing anything weird, floating up in the air or sinking, that the sum of these must equal this. So that means that the normal force plus F1 sine theta must be equal to mg. So the normal force must be equal to mg. That's what it would be if there were no pulling force, or if the pulling force were horizontal, right? But now we have this extra force making it seem lighter. So that's an expression for the normal force. Part C. Derive an expression for the coefficient of kinetic friction between the block and the surface. I think this diagram that we did here will serve us well here. The coefficient, remember, frictional force is equal to the coefficient of friction times the normal force. And since we have an expression for the normal force, we can go ahead and write that out. That's mg minus F1 sine theta. And they would like an expression for this. And also, this is not one of the variables that we're allowed to use. Remember, they're listed here. These are the things we're supposed to use. So we have to replace this with an expression for that. And here you can see how much is the block accelerating. Well, the net force on the block is equal to F1 cosine theta minus the frictional force, right? It's this pulling part in the horizontal direction minus the friction, and force net is mass times acceleration. So that gives us, are we supposed to call it? Yeah, we're supposed to call it A1, try to stick with their labels. So that's F1 cosine theta minus force of friction. And that gives us an expression for the force of friction, which would be, let's see, we'll move that over here. That would be F1 cosine theta minus mg. No, sorry, minus ma. Minus ma1. So that's moving this to this side and subtracting that over. So now we have an expression for the frictional force. And let's substitute that here. So I got F1 cosine theta minus ma1. That's the frictional force, equals coefficient of friction times mg. Ooh, should we distribute that? No, we shouldn't. Minus F1 sine theta. They want an expression for this. So coefficient of friction is F1 cosine theta minus ma1 over mg minus F1 sine theta. It's a complicated looking expression, but we don't have any numbers, so that's what it is. Part D. On the axes below, they want us to sketch graphs of the speed and displacement of the block, as functions of time if the block started from rest, x equals 0 and t equals 0. Well, this is actually maybe the easiest part, since it has a constant acceleration. Right, there's a constant net force acting on it. We found that in the last part right here. The net force is this, right, and those are both constants. So, constant forces. So, constant force means constant acceleration. So that graph, sorry, that's not supposed to look like it's curving at all. It's supposed to be a straight line. It starts at velocity 0, started from rest, and also started at position 0. So that's going to be position 0, velocity 0. I'll start out with a slope of 0 and curve upward like this. Those are the graphs. So those are, that's pretty easy points if you think about that. Part E, they want to know if the applied force is large enough, the block will lose contact with the surface. They want us to derive an expression for the magnitude of the greatest acceleration the block can have and still maintain contact with the ground. Well, let's go back to our free body diagram. When is that going to happen? The normal force has that interesting property that's as strong as it needs to be. So the normal force, as the F1 gets bigger and bigger, the sine component of it will be bigger and bigger, and the normal force will shrink, right? If there's no pulling, the normal force matches gravity. But as this increases, the normal force gets smaller and smaller, until finally we reach a point where F1 sine theta is equal to mg, and then the normal force will actually be 0. And then if we go any more than that, then F1 sine theta will be greater than mg, and that's when the box will start to lift off the ground. So acceleration max happens when mg is equal to F1 sine theta, and they want to know an expression for the magnitude of the greatest acceleration where that's going to be true. Now, acceleration here is equal to, we know that the acceleration of the block from this expression here is F1 cosine theta minus the frictional force, or minus frictional force is, the normal force here would be 0, right? So there would be no friction. So setting these two things, if we want an expression for this, I think we could just have here that A1 is equal to F1 cosine theta over m. And since F1 is one of the things that we can use, that works.